Today we're going to be learning about Hess's law. Hess's law states that if a reaction is carried out in a series of steps, the enthalpy for the overall reaction equals the sum of the enthalpy changes for the individual steps. In Hess's law problems, we're usually trying to get our smaller equations to add up to a net equation to figure out how much heat that produces. You can visualize what's happening by using this energy graph. Imagine your reactants starting up here. We have methane gas and oxygen gas at a higher energy level. If this reaction takes one pathway all the way down to its products, carbon dioxide and water, it will release 890 kilojoules. However, if it takes a different path, a two-step path, stopping first to produce carbon dioxide gas and gaseous water, then having that gaseous water turn into liquid water, also releasing heat, those two pieces add up together. Notice here how the 802 kilojoules released by this first step added together with the 88 kilojoules released by this second step add up to a total of 890 kilojoules being released by this reaction. Hess's law says that we can use the information from the two smaller reactions to find out information for our net equation. Now let's try a practice problem. In this question, we're going to calculate the enthalpy change, the delta H, for the following reaction. Here's our goal, our net equation. P4O6 solid plus 2 gaseous oxygen molecules will produce 1 P4O10 in the solid state. We're given two chunks of information. Our goal right now is to match which chemicals belong on the reactant side and which belong on the product side. I see that I have a P4O6 in my reactant side. I can look through the chemicals in my list from my two given equations, and I find that I have a P4O6 right here. When you find that you have a chemical on the wrong side of the equation, what we do is we flip the equation. I'm going to write it backwards. P4O6 solid producing P4 solid plus 3 oxygen gas. And what we do when we flip an equation is we also have to flip the sign of the enthalpy. So this enthalpy for the reaction will now be a positive 1,640.1 kilojoules per reaction. For mental bookkeeping, I then cross out my entire reaction to make sure that I don't use those numbers again. Now what I do is I look at each chemical in the question to make sure that when I add my reactions, they're going to be my goal equation. I can see that I have a P4 in the solid state on the reactant side and a P4 in the solid state on the product side. That's going to make me cancel these pieces, just like if you had a plus x on both sides of an algebraic equation, like x plus 2 equals x plus y. Our x's would cancel because there's a positive x on both sides of the equation. You can envision that like subtracting an x. Then I check my other chemicals. I see that I have my P4O6. I don't have anything to cancel, so that will end up in my final added up equation. I also see something really interesting. I see that I have 5 oxygen molecules in the gas state on the reactant side, and I have 3 oxygen molecules in the gaseous state on the product side. We end up treating this exactly like an algebraic equation. If I had 5x plus 2 equals 3x plus y, I could subtract my x's over, negative 3x minus 3x, to get 2x on the left side of that algebra equation. In chemistry, we'll just do the same thing with our chemicals. We'll have a leftover 2 oxygen gas molecules on the reactant side. Check. Those are done. The leftover molecule is the P4O10 in the solid state. To make sure that we haven't broken any rules of algebra, since I've added up these 2 equations, I also need to add the enthalpies. When we perform this calculation, we'll end up with the delta H equals negative 1,300 kilojoules per reaction. As we've seen in our examples, we can add delta H values if we're adding reactions. We can also flip the sign of delta H if we flip around a reaction. But the last thing that I want you to know that you can do is you can also multiply by an integer or a fraction. Let's say you need to multiply your reaction times 2 to be able to cancel out an unwanted chemical. You would also need to multiply your delta H by that same integer or fraction. Once you finish changing the direction of the equations or the magnitude of those equations, you'll need to add up your delta H's to get to your final answer. I hope you have found this Hess's Law video to be very helpful.